Hello again. This is Math 1120 coming to you from the College of DuPage, and the title of this lecture is Rectilinear Motion with Constant Acceleration, Part 1. As always, please be an active learner as you watch this video. We develop an expression for the velocity as a function of time for an object moving with constant acceleration. For an object that has an x component of velocity v0x at time t equals 0 and moves with a constant acceleration a sub x, the velocity v sub x at any later time t is given by v sub x is equal to v0x plus a sub x times t, and the units of this velocity will of course be meters per second. And this comes directly from the equation from the last section where we learned that the average velocity in the x direction is the difference in the velocities divided by the time. If we solve this expression for v sub x using algebra, we get this expression. So in this first example of constant accelerated motion, we'll simply consider a car that is initially traveling along a straight stretch of highway at 15 meters per second. Here's the picture of this. At t equals 0, this time, the car begins to accelerate at a constant 2.0 meters per second squared in order to pass a truck that's not here. So the acceleration begins here. It's constant in this direction at 2.0 meters per second squared. So the question asks, what is the velocity of the car after 5 seconds have elapsed? Well, the acceleration is constant during the 5-second interval, so we can use the equation we just derived. V in the x direction is v0x plus ax t. I plug in the numbers and I get 25 meters per second. Next, we want to derive an equation for the position x of a particle with constant acceleration. To do this, we make use of two different expressions for the average velocity during the time interval from t equals 0 to any later time t. So first, when the acceleration is constant and the graph of the velocity versus time is a straight line, the velocity changes at a uniform rate. So in this case, the average velocity through any time interval t is simply the average of the velocities at the beginning and at the end of the interval. Thus, for the time interval from 0 to t, we know that the average velocity in the x direction, v average x, is equal to v0x plus vx, all divided by 2. And this is true for constant acceleration. And this equation would not hold if the acceleration varied over time. So there is one equation we're going to use. We also know that Vx, the velocity at any time t, is given by the equation we just derived, which is this one. Vx is equal to V0x plus AT. So we're going to take this equation, and for this Vx here, we're going to substitute this. So there is the 2 for the 1/2. There is the V0x, and we're going to substitute this for Vx, getting this. So now we have that the velocity average in the x direction is v0x plus 1/2 ax t. But the average velocity in the x direction is also x minus x0 over t. That was from the prior lecture. So if we put x minus x0 over t here, we can solve for x, and we will get position as a function of time for an object moving with constant acceleration. For an object undergoing constant acceleration, its position at some time t is given by x is equal to its initial position x0 plus v0x times t plus 1/2 a, and then this is t squared. we multiplied both sides by t and moved the x0 over from the other equation using algebra. The units of each of these three terms are meters, and we make some additional notes. So x0 is the position at time t equals 0, v0x is the velocity at time t equals 0, ax is the acceleration, and that's assumed to be constant in time, and x is the position at any time later t. Now, for some problems, we aren't given the time interval for the motion, and we need to obtain a relationship for x, v sub x, and a sub x that doesn't contain t. By the way, some students ask me, how do I know to use this equation? That's exactly when you know to use this equation, when you don't have t in the problem. So to obtain such a relationship, we can eliminate t from some earlier equations. Now this involves some algebra, but we'll go through it, and the result is a very useful equation. Okay, so we know from a prior equation that we had in this lecture, if we solve for t, we can solve for t and say t is equal to v sub x minus v sub 0 x divided by a sub x. And then we're going to take this expression for t, and we're going to substitute in the equation that we just had everywhere where t is. So the equation that we just learned was x is equal to x sub 0 plus v0, and we had t here. We also had t squared here. So we're taking this expression for t and putting it there, and there's quite a bit of algebra, but then we will work through the algebra. And so we transfer the x0 to the left side and multiply through by 2a to get 2ax equal x minus x0 is all of this, and we will also notice that this is the negative of that, so that cancels out. And then what we're going to do is we're going to solve this for v sub x squared. So when we do that, what we're going to get is an equation that represents the velocity as a function of position for an object moving at constant acceleration. And so for an object moving in a straight line with constant acceleration ax, we have v sub x whole squared is equal to v sub 0x whole squared plus 2a times x minus x0. Now each term in this equation has units meters squared divided by seconds squared, or the square of meters per second. V sub 0x is the initial velocity of the object when it's in initial position, x0. Vx is the final velocity of the object when it is at its final position, x. And this equation generally is used in problems that neither give a time nor ask for one. This equation is generally used in problems that neither give a time t nor ask for one. I said that twice on purpose because that's very important. Please make note of that. Let's look at an example of entering the freeway. So we're going to apply our learning to a problem in which time is neither given nor asked for. A sports car is sitting at rest. That means it's not moving in a freeway entrance ramp. The driver sees a break in the traffic and floors the car's accelerator, so the car accelerates at a constant 4.9 meters per second squared as it moves in a straight line onto the freeway. What distance does a car travel in reaching a freeway speed of 30 meters per second? Well, 30 meters per second is the speed that you want to reach. So that is your final speed. Your initial speed is 0, so this equation is going to be operative. And so what we're going to be able to do is we can substitute numerical values, and we can obtain that our final speed of 30 meters per second squared minus our initial speed divided by 2 times the acceleration is equal to x minus x0. That's how far it took us to attain this 30 meters per second speed, and the answer is 92 meters. Let's look at another example. And in this example, we will, for the first time, look at constant acceleration motion of two objects moving simultaneously. And so we have a car here that is moving at a constant velocity, and then we have we'll pretend there is a policeman, I think it is a policeman actually, policewoman, who starts at rest but then chases after this person, but they're accelerating in order to catch up. So let's look at this then. Clearly we'll need to describe the position and velocity of each separately, and then use the resulting equations to answer any questions about their motion. Okay, so suppose that a motorist is traveling at a constant velocity of 15 meters per second, that's here, and passes a school crossing corner where the speed limit is 10 meters per second. Now notice they're going 15 meters per second, so they are speeding, and there's the sign where they pass. A police officer on a motorcycle stopped at the corner, so their initial velocity is 0, starts off in pursuit with a constant acceleration of 3 meters per second squared. So that's their acceleration, but they're starting from rest. And we call this x sub c for the position of the car, and this is x sub p for the motion of the policeman. Okay, so now we have equations for each of these. The policeman's equation is x0, which is 0. Their initial velocity is 0, so 0 and 0, but then it's 1/2 a t squared. So we figure out where is the position at any time t, and it is 3/2 times t squared. Now, the car is at initial position is also 0, but they have an initial velocity of 15 meters per second, but they're not accelerating. So this ends up just being 15. So now what we need to do is we need to solve this for t. So we have that 3/2 t squared. The location of the police motorcycle is the same as 15 times t. Now we have to solve this using factoring. And when we solve this using factoring, or the quadratic equation, we get 0 and t. There are two solutions. But you see, the first one corresponds to when the car passes this station, the policeman is there. That's time t equals 0. They're in the same place. The next time they'll be in the same place is when the policeman catches up. So that is going to be the 10 seconds. Okay. So 10 seconds then is the answer when the policeman catches up. Now there was a part B. We know that the officer's velocity v sub p at any time t is v sub p initial plus the acceleration times the time. And when t is 10, we put 10 in there, and it's 30 meters per second. So when the officer overtakes the car, she is traveling twice as fast as the motorist is. And part C, it was asking, so how far is the policeman, where is the policeman's location? So when t equals 10, the car's position is 150 meters, and the policeman's position also has to be 150 meters. That verifies that at the time when the officer catches the car, they've gone equal distances and are in the same position. Again, summarizing our equations of motion, please make note of these. These will be in the grace notes. And all of these are equations of motion for constant acceleration. Now we'll look at a more complex problem, and we'll use all three of our equations in doing this. So a motorcyclist is traveling east through a small Iowa town and accelerates after he passes a signpost, and the signpost is here, so that's at time t equals 0. His acceleration is constant, 4 meters per second. At time 0, he is 5 miles east of the signpost. I guess he doesn't start accelerating there. He starts accelerating when he's 5 miles past the signpost. I apologize for that. And he has a velocity that was a constant before he begins accelerating of 15 meters per second. Find his position and velocity at time t equal 2 seconds from this point. And when is the motorcycle, where is he when his velocity is 25 meters per second squared? Okay, in part A, we want to know the position and velocity, the values of x and v sub x respectively when time t equal 2 seconds. So we use this equation. So we get 5 plus 5 times 2 seconds plus 1/2, 4, t squared. We calculate and we get 43. So that gives us 43 meters. That's the position. And then for velocity, we know that the velocity is the initial velocity, which is 15 meters per second plus, and this is the acceleration times the time. That gives us 23 meters per second. Now in part B, we want to know where is the motorcycle when his velocity is 25 meters per second. Well, they didn't tell us the time, they just told us the velocity, so we're going to use this equation. So we substitute 25 here, square it, that is 15 squared, that is 2. This is a minus his initial position. We're going to solve this for x. So when we solve that equation for x, we get x is equal to 55 meters. And I think we already talked about this problem. We did already talk about that problem. Okay, so we're going to close with this final example then about the motion of a car. And the motion of a cart is moving along the x-axis, and it's described by the equation x equal minus 4t squared plus 5t minus 1, where t is time and all the constants are in SI units. What are the values of, in this order, its acceleration, its initial velocity, and its initial position? It's a multiple choice question. You know what to do. Let's see how you did. And the correct answer should be C. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. May God bless you all.